Here, first of all, the vertex is, it's not negative 12, 6, it's 6, negative 12. Be careful about the order, which is a little bit off the screen. All right, this represents 4p, which means, like, so p turns out to be a half. 2 divided by 4 is a half, which isn't horrible. This one, it'll do. I'll put it that. All right, now, we need to go half unit. Let me back up. This thing is expressed, you have like y equals x squared. I'm saying y is not squared, x is squared. If it's of this form, it's a vertical parabola. Opening which way, up or down? Up, because it's positive coefficient. And so, like I said, you need to note that. I would write it down. Just the word up, if nothing else. It opens up, which means we're going to go above the vertex to find the focus. How far above? Half a unit. And so what's half a unit above this wide value? Negative 11 and a half. Woohoo. And here, the axis, if it's vertical, the axis will be x equals that x value. The axis always goes through the vertex, and it's either the vertical line going through with that x value or the horizontal line going with that y value. And then the directrix, then, here, let me draw what I have so far. X equals 6 is over here. One decision you have to make for something like this is, do we rescale the axes? I think it'd be okay. I'm not going to bother. We're going to be a little bit off the grid, but it'll be okay. I think. Well, the catch is, you know what? I will try rescaling. So I'll say 2, 4, 6, 8. In which case, the vertex is 1, 2, 3, 1, 2, 3, 4, 5, 6. All right. But that means my focus is just half a unit above, which is not much. So it's going to be right above that. It's a little bit problematic, but I think we can deal with it. And then, look, if p is 1/2, then once again you go 2p either side. So the lattice rectum is 4p across, and 4 times 1/2 is 2, right? Yes? 4 times that's 2. And so I'm saying you're going to go 1 either way from the focus. The focus is what I plotted here. So go 1 to the right, plotted point, 1 to the left, plotted point, and it's just, once again, a quarter of a unit. Well, not a quarter, it's a half a unit, but a quarter of a space above, just above. And we're going to draw that thing. If you have 3 points, then you can draw your parabola. So from the vertex, go up through that point, and from the vertex, go up through that point. And that'll suffice. By the way, the axis was this vertical line. The directrix is a horizontal line just below the vertex. How far below? It'll be half a unit below. Yes? On either side? Because, look, those are the endpoints of the lattice rectum. And so, once again, let me draw it. Let me blow that up. On our parabola, here's the vertex, here's the focus. Whatever this is, we call that P. Actually, let me make it a bigger picture. All right. Let's say this is our directrix. Here's our focus. Where's the vertex going to be? Here. Why there? Because every point of the parabola is the same distance from that focus and from that directrix. And so the vertex is the closest of all the points, and that distance is what we call P. So what I'm saying then is, now how far is the focus from the directrix? No? You're right the first time, 2p, right? So if I go over parallel, say parallel, going through the focus, how far am I from the directrix? 2p. But if I'm on the parabola, I must be the same distance from the directrix as I am from the focus. So if I go 2p over from the focus, this point must be on the parabola because it's 2p from the directrix and 2p from the focus. That's how we get 2 good points in the parabola, is by going 2p out from the focus, either direction. And those points are called the endpoints of the lattice rectum, and they must be points in the parabola, which is why we come up with them. And then that's how we draw our parabolas. Okay? And then some of the parabolas are like this, where it's kind of just... let me just say this. Watch this. Just watch. I'm going to transform this equation to the algebra 2 form. To do that, I would take half of, and then I'd move the 12 over, minus 12. So I'd have 1/2 as a coefficient. And then the plus 12 becomes minus 12. It wouldn't be real pretty this way either. Oh, that's your other alternative. I'm just telling you. If you want to do it this way, you may. And you could use this to plot points. I'll just show you real quick. I'm not going to redraw the thing. But I'm saying, normally, with a normal plain old parabola, what I was saying yesterday, is you say, okay, 0 squared is 0, then 1 squared, 2 squared, like that. And these get the same numbers, even though they're negative, right? And then you apply your transformation. Well, this 1/2 here is a vertical compression by a factor 1/2, which means the normal numbers you normally plot get compressed by a factor 1/2, which this one's actually doable. Maybe I should have done it this way. And what this represents is not hard coordinates, but actually, from the vertex. Well, here, I'll just show you real quick. The vertex is at 6, -12. Which is here. Mind you, we're going by 2s. This is -12, this is 6. And so I did this way. 0, 0 represents the vertex. I'm going to skip this one and use this one. 2, 2. Well, I'd go over 2 and up 2, which is actually 1.1 point. And go left 2 and up 2, which is here and here. Actually, that worked out much nicer. So I'm saying that's your alternative. Usually, as a general rule, we want to work with the whole numbers. So I'm saying, for the most part, if this form, the algebra 2 form, has a fraction, then it'd be better to do it the way we're showing you. Okay? This is the exception. Starting on all these, like here, if I wrote this as an algebra 2 equation, you'd have 1/24th. Y plus 5 squared, d plus 1. You wouldn't want to do this method with a coefficient of 1/24th. Okay? So I'm saying most of the problems, you want to use the endpoints of the lattice rectum, the new approach. That's why it's the kind of problems we're going to throw at you. But some of them you might want to choose the old way. All right, look at number B. No, we did BB. Someone pick one problem. I'm going to do one of these. So before, up to CC, from that page up to CC. Pick one. Okay? Once again, the goal is simply to write an equation, draw a sketch. You don't have to. I'm not going to take off if you don't. But your likelihood of getting it wrong goes up dramatically. I'm just telling you. Draw a sketch. All right, -7, -2 is your vertex. Put it there. The directrix is a vertical line. Where is this line in relation to that vertex? It's vertical, so it's either left or right of. Isn't this a bigger x value than that? It's actually to the right of. Yeah, AA. Now, so that's your picture. Which way does this thing open? To the left. And that's the biggest thing the sketch is supposed to get you, is that it's a leftward opening parabola. Like I said, if you don't get that right, you're getting the wrong form of the equation. Now, is the coefficient positive or negative? Negative. I would get that correct as soon as possible. Now, if it's horizontal, it's going to be of the form x equals y squared. So it's x minus h here. Over here, it's going to be y minus k squared. The coefficient's negative. I'll put that here now so I can't forget. Now, what is P? And it's the distance from the vertex to the directrix, or the focus. How far is this point from that line? 1, right? -7. That x value is 1 away from that value. I'm going to rephrase my definition, and listen to me. I've always maintained that P is a distance, and therefore it's always positive. Okay? But, for the sake of getting this sign right, because people always forget to put a negative sign, I'm going to rephrase it. I'm going to say P represents how you get from the vertex to the focus. Which is almost the same thing, but not quite. So how would you get from the vertex to the focus? You'd go left 1, wouldn't you? So I'm going to say p is a -1. And then if this coefficient is always 4p, that means it's actually -4. I'm never going to ask what p is, or if I do, I'll take whether you put positive or negative, frankly. I don't greatly care. What I do care about is that you don't forget the negative sign in the equation. And that's what people always forget, even me. Okay? And besides which, the problem we're going to do next, p being a negative, is going to be necessary. All right. By the way, what goes here? Plus 7, because this is h and k, and you do x minus the -7 is plus 7, and then this is y plus 2, and we're done. Questions? All right, then let's look at 36. And frankly, I never did a problem like this before now. For yesterday, I guess. We used to have problems where they gave you the vertex, which actually is an easier problem. All right, first of all, let's see if we can get a picture drawn. The focus is thereabouts, and the axis is a vertical line, so draw a vertical line through that focus. So like, there's my focus, here's the axis. And the point of parabola is somewhere over here, and there's some point of parabola. Fine. Now, the funny thing about this problem is I always kind of assumed that this was an upward spacing parabola. Okay, the vertex is somewhere down here, and then it goes up through that point. But then I started thinking about it. It doesn't say the parabola opens up. It just doesn't. It just says it's vertical. It is possible to have the parabola be going this way, and that's still avoiding the parabola. And you'll see in algebra we'll get two different answers. They're both possible in this case. Okay, so like the next problem, I think, is like this. The problem after that, it says it opens up or down, so you'll get one answer. But here, we're going to get two answers, technically. Now, let me write out the form. If it's a vertical parabola, we know that much because the axis is vertical. Then you'll have y minus k over here and x minus h squared over here. It's a y equals x squared type of parabola. It's vertical. And then the coefficient is 4p. And p could be positive or negative. That's how we get one going up or maybe going down. Now, this is a little bit tricky. We need to plug things in. First of all, you need to realize, look, we don't know where the directrix is. We don't know where the vertex is. We have no way of calculating p, like knowing p from the problem. And so p is going to remain an unknown in this. We're going to be solving for p. X and y, we're going to plug in. We're given an x and y. If you're ever given a point on the graph, then I'm saying you plug them in for x and y. Now, the vertex, this is a little bit tricky. I'm going to pretend the vertex is below. I need to put it somewhere in the picture, okay? I know something about the vertex, and here, let's write this down. The vertex, I want coordinates for this thing. Don't I know it's on the same axis? I mean, it's on the axis of symmetry. So I know the x value must be 3, just like it is for the focus. The y value, though, I don't know. This distance we call p, don't we? So how would you express, here, I'll put it here. How would you express this y coordinate in terms of this y coordinate? Perfect. Yes? And first of all, x equals 3 goes here. And before I put that, look, when I first saw this problem, I got it set up like this, and you have two unknowns, and it just isn't workable with two unknowns. You need one unknown. And so, frankly, I looked it up. Come on. Oh, I lost it. All right, and you put parentheses, 3 minus p. And don't forget the parentheses, they're necessary. Because we're subtracting k, and now we're subtracting that binomial. And now it's just algebra. We solve for p. First of all, I'm going to clean up what's inside of here. If you distribute the minus sign, you get minus 3 and plus p. See how the parentheses were critical? That really is just 15 plus p, yes? And now you can distribute the 4p. What's 4 times 15? So 60p plus p, 4p squared. All right, that's cleaned up. Over here, that's just 20 squared, which is what? 400. Good. All right, we have a quadratic. Let's bring everything to the left side. 400 becomes a minus 400, which looks horrible until you realize you can divide all those by 4. And by the way, 60 divided by 4 is 15, because we just got the 60 by multiplying by 4, didn't we? So it's actually not that bad. All right, there you go. Back to that. Bless you. What'd you get? Numbers that multiply by 100, which, just for the record, like 10 times 10, that's not right. Yeah. 4 times 25, not good. Actually, I already skipped over, didn't I? 5 times 20. Those numbers multiply by 100, but they have a difference of 15. So look at that to know the right numbers, but look at this to know the right signs. Which one's negative? The 5. So there you go. P minus 5 is one factor, P plus 20 is the other factor. So each of those factors equals 0 and solid, you get that, you find that the missing number here is 5, that makes it 0, and then this number here is negative 20. And we get 2 possible parabolas, okay, because we have 2 different possible values for P. So to write your equations, if P is 5, then the vertex is where? 3 comma what? Right, 3 minus 5 is negative 2. So let's write that equation. And I already have my form here. 4p is 20, right? And then I do y minus negative 2, y plus 2 equals x minus 3 squared. There, that's one possibility. If I do that parabola, which way would it open? Up, okay? And so that would be the one that you kind of normally think of, but it is not the only possibility. Now, let's do the same thing. If p is negative 20, then the vertex is 3 comma 3 minus p. What's 3 minus negative 20? 23. Then what goes here in the equation? If p is negative 20, it's 4p. So wouldn't want to have to draw this thing, I think. But, and then y minus 23 equals, and then x minus 3 squared. Same axis, but definitely a different parabola with a different vertex, and this one opens down. And if you were to write both these equations as y equals, so you can punch them in the calculator, what you'd see is something like that, where the 2 parabolas have the same focus, different vertices, but they both go through the point that was given. They're both possible. Okay, so these problems are kind of different, to say the least. You can say they're a pain. But there you go. And like I said, the key with something like this is working out, how to use what you're given to express this in terms of one variable. And the real key was realizing you can express that y value in terms of p. Because until you realize that, you're stuck. Okay? All right. You have a note sheet you picked up? If you didn't, go get it quickly. So we're now talking about parametric equations, which this is only, maybe this stuff is new, but this is very different because it's a really different kind of equation. And so let me try to explain the idea behind parametrics first. First, our normal equation just have x and y. Parametrics, you have x, y, and t, where t typically represents time. And so instead of describing how y changes based on x, or how y is related to x, instead you express x in terms of t and y in terms of t. T is called the parameter. That's why they're called parametric equations. And one key idea here, watch this for a second. Let me explain one huge purpose of this. First of all, if I were to draw this, can you tell me what shape I would get if I drew that? I'll give you a clue. That, if I wrote it as polar, is the same as r squared, isn't it? And if I take square root of both sides, I get r equals plus or minus 3. And it's r equals 3 is a circle with a radius of 3. R equals negative 3 is actually the same circle, just it draws it differently, a different starting point, but the same circle. So I'm just saying, this is the equation for a circle. And a circle is not a function, as in y is not a function of x. It fails the vertical line test, yes? But watch this. You don't have to know this yet, but you will know that the parametric equations for a circle look like this. And for this circle, oh, I messed up last period. I don't think I got this part right. Well, there you go. There's the parametric equation for that circle. The important point here is that x is now expressed as a function of t, and y is a function of t. And when you get to calculus, it's all about dealing with functions. And so we've taken a problem where it was not a function, express it so it is functions. And now it's doable. Okay, so that's one of the main motivations for doing parametrics. Now, one more thing I want you to notice is, one thing is, it's easy to convert between these. It can be tricky at times, but here it's really simplistic. To get from here to here, you basically said, well, I'm just going to call x t, and in this equation replace x with t, and boom, I have my parametric equations. Or conversely, here just say, okay, if t equals x, I can replace t with x here, and you have your rectangular equation. So go back and forth isn't hard, typically. Like I said, it can be tricky, but that's the easiest way. One more thing I want you to notice is, like, look at the table. At t equals 0, you got these coordinates. In fact, when we draw these, one thing you have to get used to is we talk about motion on the graph. And we'll talk about the starting point and the direction we go on the graph. And at t equals 1, you're further over. T equals 2, you're further over. So that's why that arrow is going in that direction. So I'm saying you talk about motion along the graph. It didn't have restriction, so this really should be the whole line. T could be negative. So I'm saying without the restriction, it surely should be the whole line, okay? But they restricted t, and that can happen, so you just get part of the line. Watch this, though. If I change this so it was t cubed here and t cubed here, I would have the same graph, except it would move faster. If you graphed it, and if you put 1 and y2, and you can draw a parametric something calculator, I'll show you sometime. If you go to mode, where we change to polar mode, change to parametric mode instead. It's really that easy. And I'll show you sometime, but I'm saying these parametric equations are for the same graph, but if you graph them side by side, you'd see, then they'd be graphing on top of each other. But this one would win the race, so to speak. It would draw it faster. So anyway, all right. Now, here's your formulas, sort of. And I say sort of because, look, if you're given what is this, vertical parabola? If you're given a vertical parabola, all you need to do to get parametrics is, like I said, replace the x's here with t's and say that, okay? And if it's horizontal, where x is a function of y, then replace y's with t and say you replace y equals t with t, and you have parametric equations. That's not the only way to do it, but that's the easiest way to do it. And so if you're asked to find parametric equations, just write that and you're good. All right, let's get to work. Now, first thing we're going to do before we draw it is go ahead and convert this to rectangular. And like I said, it's something as simple as this. All you're doing is replacing t with x here. And so you get y equals 2x squared plus 4x plus 1. And this is your rectangular equation. You're done. Sort of. I say sort of because it didn't just say to do that. It said to graph the equation. And so while if it just said rectangular form, I would accept this. This is rectangular. Rectangular just means there's x and y's only. There's no t, okay? But we need to get this in graphing form, which means we need to talk about completing the square. So I'm going to move the 1 over, do that. This is supposed to be tomorrow's lesson, but you get a little preview. we factor out the 2, and then we just complete the squares. It's different from what was on the completed square worksheet because you only complete the square on the x's because it's a parabola. But the same skill. This becomes x plus what squared? Okay, I said it. I further than wrote the answer. You're right. And then what goes here? 1. Right? Because look, what goes there is the right constant so that this equals that. And if you did x plus 1 times itself, you would get x squared plus 2x plus 1. What goes over here? No. No. Look, what do we add over here? A 1 doubled. So yes, plus 2. Be very, very careful about that. Whatever you add in here to complete the square, you need to multiply by this coefficient to know what you're really adding to that side. That's what you really need to add to the other side. Okay? Now, let me get this back being blue. This side is just y plus 1 now. The coefficient 2 is still there. And one more thing, with the form we're using, the coefficient we're going to put over here. So there's our graphing form. Here's the thing though. Like here, that's 4p. So what is p? If 4p is 1/2, then p is 1/8. You take a fourth of a half, you get an eighth. I'm not doing it that way. So like I said, you have options. You needed to get it into some graphing form. I'm going to rewrite it algebra 2 way. Take this and just solve for y. You get y equals 2 times x plus 1 squared and then minus 1. That's a nice form as well. It's algebra 2 form. The coefficient of 2, that's much more doable. Okay? You really want to work with a whole number there, if at all possible. So, let me explain, first of all, the vertex. Where's the vertex? Right? And if you look at this, you just take the opposite of both these. You look at this form, you take the opposite of the x, but you actually use the y value as this. Okay? So either way, that's the correct vertex. Plot that. And then, like I said, I'm just going to use this equation. Let me explain this again. Watch. So I'm going to make a little table. If you just do a normal parabola, it's plain x squared, and then you square these numbers, you get this. But it's 2x squared, so you double that. It's vertical expansion by a factor of 2. So what you normally would have done, you double. So what I'm saying then is, watch this. Like here, if I'm 1 away from the vertex, if I'm 1 away either side, I would normally go 1 squared is 1, put the point here, but it's doubled, so the y value is 2 above the vertex. And then if I'm 2 either side of the vertex, normally I'd go 2 away, and then 2 squared is 4 above, but the 4 got doubled, so the y value is 8 above. And the symmetric point goes there, and you draw your parabola. So I'm saying that's how I want you to draw a parabola like this, the old way, the algebra 2 way. The last rectum is 4p across. 4 times an 8 is a half. Just imagine, like I said, the new way of doing it, when it's usable, is to go this far. You go 1/8 unit above the vertex, and then you go, that's all the way across. So you go a 1/4 unit either side, plot a point, 1/4 unit the other side, plot a point. That's not going to be, that's worthless. You're not going to get a good graph out of that. I guess unless you really rescaled everything, blow it up so you're dealing with fractions, but just don't. This isn't really usable here, is what I'm saying. Okay? Okay, next. Look, we want to get a rectangular equation. So first of all, you need to replace t, but that means you need to solve for t. So t equals y over 3. And place a t in this equation. So you get y over 3 squared plus 4 times y over 3. Now this is y squared over 9. I'm going to rewrite it, put the 9 under the 2 actually. Is that okay? And then this is just 4/3 times y. So here's the deal. With a coefficient like that, I don't really want to attempt to get graphing form. I'm going to make a table instead. Okay? You had to get it to rectangular. We got this. This is definitely a horizontal parabola that opens to the right. Yes? And that's important to note because it'll guide you when you start plotting points from your table. But let's make a table. In your table, you need a t, an x, and a y. You know what? I forgot something. Sorry. Got to get back in the habit. When you draw graphs based on parametric equations, and I know I was using this, but ultimately we're trying to graph what this shows. My point is, you need to figure out the starting point. So here, I'm going to kind of make a table. If I plug in t equals 0, write this down, into the parametrics, so you get 0 here for the x, and you get 1 for the y. I want you to label that point on your graph as the starting point. So I'm saying parametrics, you need to draw the graph, yes, but also indicate the motion, where you'd start at time 0 and which way you go. To figure out which way you go, you should plot one more point. At time 1, which is later, what point do you get? Well, actually, you don't even need to calculate it. It's to the right, isn't it? So that's all you really need is which way you're going. And I'll just tell you, it's not always the case that you go to the right on a parabola like this. You can sometimes go the other way. But there you go. So here, I want to make sure I plug in time equals 0 in my table. If I plug in 0 here, what is y? Three times 0 is 0, yes. Thank you. What about here? Also 0, yes. So put it on your graph. And go ahead and label that t equals 0. You can't forget. Let's go and plug in 1, see what happens. Y is easier. I get 3. What do we get for x when I plug in 1 for t? Yeah, 6, right? 1 squared is 1 times 2 is 2. This becomes 4. 2 plus 4 is 6 for the x value. Plot that point. 1, 2, 3, 4, 5, 6, 3. That was t equals 1. Come on now. Now, it looks right now like maybe it's going, we already know it's still shows on the right. My point is, it seems like if I keep going, I'm going to get something too big. I'm going to go backwards. Let's try -1, see what happens. So if you plug in -1, the y value is -3. You figure out the x value that you get. What'd you get? No. I made the same mistake initially. Look, this becomes +2 when you plug in -1, doesn't it? So it's 2 minus 4 is -2. All right, let's try -2. This way seems to be promising. Plug in -2 here. The y value is -6. And I'll leave it to you to figure out the x value you get from here. Don't say it, just figure it out. What'd you get? Zero's correct. Look, -2 squared is 4, so that's 8. But -2 here makes it -8, so that's why it works out to 0. That's here. Now look at it. You see that we have our symmetry now? This actually is the vertex right here. This point, probably the axis goes along here. And so this is 6 above, goes 6 below. And draw your parabola. And how do I indicate the direction of motion? Going up or going down? time 0 is here, time 1 is here, so I'd say I'm going up on the parabola. See what I'm saying? All you have to do is one arrow, but one's better, I would say. All right, let's try this one. This one, it says nothing about rectangular equations. I'm just going to use the table. And I want you to realize, the last one, I had to get a rectangular equation, but I didn't have to actually use it to draw the graph. I didn't convert this to parametric. No, I mean graphing form, standard form. Listen, I'm not even rewrite the equation at all. I just make a table, and I'm going to plug in -3, -2, all the way up, from -3 to +3. So this one does have a restriction, so we won't get an entire parabola. I can't remember, frankly, if I did that right last period. If I drew the whole parabola, like beyond what I should have or not. But this one will have endpoints. Now, exercises are easy. So let's do that first. -3 squared is 9, -1 is 8. -2 squared gives you what? -1 is... And then -1 plugged in is 0, gives you -1. And then when you plug in these positives, you get the same answer as these negatives. 1 squared is 1, -1 is 0, 2 squared is 4, -1 is 3. Here you get 8 again. Okay? I don't know why I have T here. It should be Y. Is that what you guys are talking about? Now, this seems kind of weird. If I plug in -3, I get -3/4 here. 2 minus 3/4 is 1 1/4. And it just is. I plug in -2. I get -1/2. 2/4 is a half. 2 minus a half is 1 1/2. 1/4. 2 minus a fourth is 1 3/4. Are you with me? What goes here? When I plug in 0, I get 2. Then I plug in 1. That's a fourth, 2 1/4. And it's really just going by fourths. So it's 2 1/2 and 2 3/4. Seems kind of weird. Now let's start plotting points. I'll just start with this one. And be careful with this. These are your coordinates over here, right? In other words, these are not x values. So just, 8, 1 1/4. Go over here to 8. Go up to 1 1/4. Just estimate. There's 1 1/4. Then 3, 1 1/2. Here's 3. 1 1/2 would be halfway between 1 and 2. It's not that bad. When you're at 0, you're 1 3/4 is close to 2. Then when you're at -1, you're up to 2. And then you start going back. You're back to 0, and now you're 2 1/4. And hopefully you start seeing the symmetry. When you're back to 3, you're at 2 1/2. You're half a unit above the middle. And here you're 2 3/4. You're 3/4 of a unit above the middle. And so you have a very, very narrow parabola opening to the right. Now listen, I didn't rewrite this as a rectangular equation because I didn't have to. But ultimately, what you'd have to do is solve for t, but you'd get y plugged in here somehow. And so ultimately, it's of the form x equals y squared. It is a parabola that opens to the right. You could have at least known it as horizontal by looking at this. Almost forgot. Where am I at time 0? Actually, at the vertex. Doesn't always happen that way, but it did in this case. And at time 1, I was at which point here? Top or bottom? The top, yeah. And so the motion is in that direction along the parabola. Direction going up on the parabola. All right, one more. Fortunately, it's easy. Quick. Now, I say that, but don't go so fast that you mess it up. You want to start with rectangle, write parametrics. Remember what I said though. Your parametrics should be always such that x is a function of t and y is a function of t. So what I would do is take your rectangular, express it, make it so x is expressed as a function of y, or y is a function of t. I mean x. In other words, solve for x, if you, solve for x or solve for y. Do that first. That's easy. Just replace y with t. So you're going to put t in place of y there. And then basically say that you replaced y with t, and you're done. It is that easy. Okay? But like I said, you're supposed to express x and y as functions of t. So if you just put t here and wrote this as one of your parametrics, I'm not going to give you full credit because it's not expressed as a function. Let's draw this thing. Now I'm just going to go back to this. Where's the vertex? Plot that. What's p? Evelyn? If your coefficient is 8, then what's p? Is Evelyn awake? Okay. Couldn't tell. This represents 4p, so p is 2. And positive 2 means you're going, let me back up. Which way does this thing even go, Jeremy? Be careful. It's horizontal, so actually to the right. Because this is the form x equals y squared, it's a horizontal parabola. Because of the positive, that means you go to the right. To the right, then, is the focus. And then from the focus, you go, that was p that took us there. You go 2p above, which is 4. 2p below, which is 4 below. And draw your parabola. That's how quick it should be. Once again, if p is 2, this distance was 4, because it's 2p, this distance is 4. So how long is the lattice rectum from endpoint to endpoint? 8, which is 4p, which that coefficient will be the endpoint of the lattice rectum, except this really is the distance. You better not put a negative there. Otherwise, that coefficient does give you that. We're done. Question? It depends. Look. If you're using the endpoints of lattice rectum, then that's good. Vertex, endpoints of lattice rectum, 3 points, that's enough. If you're using the other skill I showed you, then 3 minimum, but you can usually do 5. Generally with this, I expect 5. Okay? By the way, I did forget this again. The starting point direction. And frankly, you're going to base this on your parametrics that you wrote. I mean, saying if you're graphing parametric equations, then I need to see starting point direction. So t equals 0. So plug in 0 here. You got to be careful with this. If t is 0, what does this become? Negative 1 squared is 1. So that's 8. Comma 0. Something doesn't compute. I mean, 5 comma 0 would be here, wouldn't it? And say again. I'm not. Oh, wait. You know what? I messed up. Look. Here's the problem. This thing isn't in the right form. The coefficient's on the wrong side. If your equation is in this form, then that's 4p. Which means p was not 2. If 4p is the eighth, to find p, you take a fourth, 1/32. I don't think we're doing it that way. Okay? So, all right. Let's back up. This is not that bad. The vertex is still 1. Okay? Now watch. We know it opens to the right. That hasn't changed. And, like I said, here, let's make a little table. Like I said, if you just did, here, I'll use this. And this is supposed to be x. This is normal parabola. With a coefficient like that, what I'm saying is I'm not using this. I'm going to go back and say it's a coefficient of 8 over here. And so you just multiply those by 8. You get 32 there, which we won't use, but this is usable. You don't have to draw this every time. I probably won't draw it again. I'm just saying, 1 squared is 1. Octupled is 8. This first point should be 8 to the right. And up, exactly. And up here, 1 squared is 1 normal, but it's expanded by a factor of 8, so that's also 8 to the right. I probably should have been skinny, not wide, because we had the coefficient in the wrong place. So, first period, lost the notes because I messed up that last class. So this is t equals 0, right? And if you plug in t equals 1, the y value is 1, which would be this point here, right? So the motion is this way along the parabola. Yeah. No. It was 1/32 away. Oh, wait, one more thing. Notice I did it again. Right here, the restriction was -3 to 3. That means I should not have gone past. I'm just making one mistake after another. I'm just saying, get rid of the arrows. It starts and stops at those points. The table, that encompasses the whole thing.